Okay, so today is really about number theory, and that includes multiples, factors, divisibility rules, prime and composite numbers, powers, digital roots, etc. So there's a lot to be covered in today's session, but I'll hopefully get through it all. So before we start, I just want to respectfully acknowledge that we are located on traditional lands across the province of Alberta on Treaty 4, 6, 7, 8, and 10 territories, the traveling route, gathering place, and meeting grounds for Indigenous peoples whose histories, languages, cultures, and traditions continue to influence our vibrant community. We recognize the land as an act of reconciliation and gratitude to those whose territory we reside on or are visiting. Honoring the land in this way acknowledges the story of the creation of this country in a way that has been historically missing. So I'm not even going to go through this because you know me already. And learning, if we look at the learning outcomes, how the number theory progresses over the curriculum, the new curriculum, it starts off with grade 3, where we learn to understand what is multiplication, and we start going through the basic facts to 10 times 10. And then in grade 4, I should actually ask you guys what grades you do teach so that I can maybe make sure I cover those. Grade 4, Sarah, Carolyn, Lexi is 4 to 7. Okay, grade 6. Okay. So what happens grade 4 is we start talking about the prime and composite numbers. What are they? And that really is the foundation for building the divisibility tests, and also to determine divisibility of natural numbers. If they understand what the composite numbers are, then they can understand what the factors are. And then in grade 6, we talk about prime factorizations and powers and exponents. So students that are this year in grade 5 or 6 will have no prior learnings of factors, multiples, primes, and composites. So those of you who are teaching grade 5 and 6 this year, you need to know that they have missed that from the grade 4 outcomes. They didn't have that last year in the old grade 4. So this is something that is new for them, and you will need to go through it. So if we look at it, the curriculum, N3 is that they explain the properties of prime and composite numbers using multiplication and division. In grade 5, they determine the divisibility of natural numbers. And in grade 6, they analyze using prime factorization and exponentation. So and then I'm just going to go through some of these things to really explain what is a factor, what's a divisor, what are some of the common vocabulary you need to know, and why division by 0 is not possible. So again, one of the things that you'll note is that on the curriculum, under skills and procedures, you're going to see some active verbs for students, things that they will be able to do after they finish this your grade or your curriculum. And the big word in this one is determine, describe, recognize, investigate, compose, and express. And those are different. Those words under skills and procedures do have a different meaning. And so I really want to thank my friend Tammy, who spent such a huge time working on these active verbs, and these action verbs, I mean. And what she did is she put out together a whole document full of what does it mean when you read that, what does it, how to define that in terms of mathematics. So in grade 4, that's you, Sarah. I know that you reached out a couple of weeks ago saying you started this and it wasn't going so good. and I'm really sorry that I wasn't able to do this with you then, but you know, you have to know something. I was reading a book, actually. It's called Limitless Minds. if you've not read that book, it is amazing. It is amazing. And the reason I'm bringing it up is I just finished it today on my walk. I do a lot of audiobooks, and I finished it. And while I was reading it, I was actually thinking of you today, because in there it says, don't ever be afraid to tell someone that you're just learning about something yourself. And don't be afraid to tell someone that you're not the know-it-all in all of this. And so you need to know, I'm telling you right now, this session, I've worked on it for the last week and I have learned so much. Again, I've learned all these activities that I could have used when I was teaching my students that I wish I would have had then. And so I'm going to be sharing a lot of these activities with you. But if you have questions, please don't be afraid to ask. But please know that I may not have the answer, but I will try to find the answers for you. But that book is from Joe Bowler, and it's an amazing book. And I think every single human being should read it or listen to it at least. It is also, it's just about the positive what happens when we believe in ourselves, when we believe in our students, and when we believe that our brain is constantly growing and that we learn from mistakes. And so when we actually, one of the things is when we make a mistake, and we know why we made the mistake, we know why it was a mistake, we actually get to the point where we learn not to make that same mistake again. But if we continue to make the same mistake, it means that we don't know we're making it. So we do want to help people with that. But anyway, let's get on with prime and composite numbers. So this is an example of what comes from Tammy's action verbs. So this is an example. It's explain, and it means to describe the how or the why of something, giving the cause or reason for why it happens. So kids, when we have an outcome that says that we need to explain, that means that they should be able to tell us why it's happening. Okay. So one of the definitions that we should know right away is factor. And one of the things I also want to let you know is in the program of studies, and that is, if you look on that sheet that I shared with you, it is 1, 2, 3, 4, the fifth link. It's called the ARPDC Interactive Math and Financial Literacy Number document. If you click on that, you'll find words, the curriculum, and it actually has links to definitions to some words, like factor, for example. So factor is a natural number that exactly divides a given natural number. And so it is something that we can multiply factors to give us a product. And we can also divide a number by a factor to give us the other factor. And so I really like this. And when you go to this link, what it'll do is it'll take you to the Learn Alberta. And can you see that I just went to the webpage? Okay. And what I really like to do is enter, you can actually use this on your board, and you can say enter a natural number less than or equal to 10,000. So let's say I can put in the number 524. And what'll happen is it will give me all of the factors for 524. And then I can say enter a natural number in the text, but to see if it is a factor, no, because it doesn't divide into it. And I don't want to see it. I don't want to say evenly. It divides, it does not divide into a number without a remainder. So we have to be careful. We do not say evenly. And so if I wanted to say 2, yes, because there is no remainder. So definitely 2 is a factor. And I can put in any number and it will tell me why it is or isn't. So that is a really great thing that you can use to help kids with seeing things. So if they have this link, they can also check for factors. But I don't want them to really go into this and use this right away, because then it just gives them all the answers. We want them to be able to go there after they know how to find factors. They can go here to check, did they find all the factors? Okay. But it's a great little thing that you can use. Okay, the other thing is there's some words that I want to make sure that we all are aware of, and you would find the definition in that vocabulary, in that interactive vocabulary. And so product is the result of multiplying two or more factors together. Prime numbers has only two factors, one and itself. And then I'm going to give you I'm going to show you activities that you can use to find prime numbers. Composite numbers is the natural number that has three or more factors. And so again, a natural number is any number from one. It's a positive whole number for one and more. Okay. And multiple is a natural number that is a product of a given natural number and another natural number. So those are some words that we really want to make sure that kids are fluent in. Okay, so then what I meant by when we multiply two factors together, we get a product. Okay, this is what it means. A factor times a factor will give you a product. And so this would be a great thing to have on your word wall, just to show kids that, so that I really believe in visuals that help kids see things and understand some of the words that we are using. I'm a real believer in games, and this is a game that is found on what's it called? Illuminations. And not everything is free, but this one is free. And I'm just going to go there for a second just to show you. It's a factor game. And what you can do is you can say, okay, well, how many rows do I want? I might want, I don't understand why they say that's rows, because those are columns. So I can have, 6 columns, and I can have 5 rows or whatever. And that means that I'm just going to be looking for factors up to 25. And so you can play alone as one player, or you can play 2 players, and you can challenge each other. So player number 1, you choose the number. So for example, I can choose 10, and then it goes to player 2, and player number 2 has to find all the factors of 10. And so they say, okay, it's 1, 2, and if they choose something, it says, no, it's not. And then I can say 5, and I say, okay. And so player 2 has scored 8. And now it says, player 2, you choose a number. And I can choose, let's say, 24. And I could say, okay, so now player 1, you have to choose all the factors of 24. And so I will say 1, 2, 3, 4, 6, 3 times 8, 2 times 12, 1 times 24. Oh, no, sorry, it's not. Okay. And I got 43. And you can keep playing. This is or if you wanted to, as just to make this easier, you can actually just make a grid that is 5 by 5 or 6 by 6 or 7 by 7, and you can use bingo chips, and they can just play that way. But I like this because it does give you the score, and you would have to look up how you do score on this. Okay, this is a really nice thing just to pick factors, like what numbers go into the number. Okay, then the other thing is prime numbers. And prime numbers is a number that only has 2 factors. And so when we only have 2 factors, it is 1 and itself. And I like this poster because it's prime equals to I and me, PR equals one and me, but it's just one and itself. And this is great. And now when I was teaching, I always did the sieve of Eristhenes. Still can't say that word. And I'm just going to go to this one here just to show you where it is and what it looks like. And so you could do this on your board and you can say, okay, set the mode, paint multiples, show multiples of a number. So for example, I can just go multiples, split colors, and if I say, I did this already, multiples of 2, and it'll automatically color them in. And so this is great because it just works on, we know that if it is a multiple of a number, then it is not a prime number, right? And so if I wanted now to go to yellow and I choose the multiples of 3, so this is something I would use on my smart board while the kids are coloring in their own sieve. So what they're doing is they are going to be coloring until they are just left with the prime numbers. And so the next prime number, well, it's not 4 because it's already colored in. And I'm going to say it's 5. And so now what happens is all of the multiples of 5 get colored in, but you'll notice that, oh, I wanted the split colors. I don't know why it didn't do that. Oh, there. Okay. Do you notice when I said split colors, you can see that 10 is also a multiple of 2 and 5. And 30 is a multiple of 2, 3, and 5. Okay, so the next, what is the next prime number? It's 7. So I'm just going to pick a different color. It is 7. And watch. And this is actually really good for also finding the greatest common factor. I'm not the greatest common factor, the lowest common multiple. Okay, so then I can go, now what's the next prime number? Well, it would be 11. And so I'm just going to pick another color and go to the ones of 11. And I can do this. And then next one would be the 13. And then 17. And then 19. And then next common, the next one is 23. And then we can have, the next one would be 29. And I can keep going. And I can, now I'd have to start reusing colors. So let's just choose green for 31. And then how about this dark blue one for 37? And of course, and I would just keep going and going. And what happens is I end up with a chart that looks like that, where all of the prime numbers have been brought to the top. They are the ones that are complete white with a little color around, and all of the other ones are composite numbers, meaning that they are multiples of other numbers. Okay? Does that make sense? So after that, then I had an aha moment. And when I was reading a book by, because I don't know if I ever told you this in my sessions, but I love Marion Small, and I love John Van de Waal. And so I was reading this book, Big Ideas, and one of the things that she, in her book, had an idea for teachers how to teach prime numbers. And so what she did was she said, give them a hundreds chart or 120 chart that only has 6 columns. And she says, because there's a pattern that happens that you don't see when you do the sieve Erasmus. You don't see it there because it is it has 10 columns. But when you only use 6 columns, something happens. And then I thought to myself, okay, how come I didn't know this in all the years that I taught? Here's what happens. Like, do you know what's going to happen, by the way? Do you know this one? Anyone here know what happened? That something is very obvious with prime numbers? Okay, then let's watch. Let's see. So I did it using, and I gave you the link. I did use a chart that I could make with only 6 columns. And so here are all of the factors, multiples of 2 colored in. Okay, so the next whole number, the next prime number is what? 3. So when I color in all 3s, this is what happens. Now, are you noticing anything? Are you noticing that the only possible numbers, prime numbers after 2 or 3, have to be a number that is one less than a multiple of 6 or one more than a multiple of 6? I didn't know that. And so then I started doing, okay, well, let's see how far this goes. And so what's the next whole number? What's the next prime? A 5. So here's 5. Yeah, it's narrowing them down, but there. Now the next prime number is a 7. So here's all of the multiples of 7. But you notice that the next prime number is 1 less than a multiple of 6, 1 less than 12, and it's 11. And here's all the multiples of 11. The next prime number is going to be a either 1 less or 1 more than a multiple of 12. So it's going to be 13. And here's all the multiples of 13. So now I can see the next multiple on the next prime number is 17. Here's all the multiples of 17. And then again, 1 more than 18 is 19. 1 less than 24 is 23. Now, 1 more than 25, 24 is 25, and we can already see that that is 5 times 5. So it is not a prime number. So then the next one's going to be a 30. 1 less than 30 is 29. And then 31, and then 37, 41, 43, 47, 53, 59, 61, and there's all the rest of the prime numbers up to 120. And I thought, wow. So the first thing, like, let's say we had a number, and I'm just choosing a number in my head right now. Like, if you said 640, and let's say I said, no, let's choose 666. Well, 666 we know is a multiple of 6, right? So we would know that 665 or 667 could be prime numbers, right? We would know that 664 definitely wouldn't be because it's 2 less than 666. But 665 could be. But then knowing divisibility rules, it ends in a 5, right? So we know that that one's not a prime number. And it's just a way that we could use, do tests to see if it's a prime number or not. But really, honestly, when we are asking kids 666, and let's just go to this one here. And then if I say, well, here's all of the numbers for factors of 666, I'm going to go 665. Well, no, that can't be a prime number because of, right? But let's go to 667. And it's not all either. And so my whole thing is, if you're going to be giving kids numbers like 667, why would you in the first place be giving numbers like 667? But if they are, then go to this glossary and use this to see if it is. And then you could say, well, it might be because it is 1 less than 666, which is a multiple of 6. But honestly, you know what? That's just so much work. But you could definitely go there. So then, anyway, I love, this was a real aha for me. And you need to know that I was overwhelmed when I was seeing this, because I was just seeing that you can, first of all, ask yourself, is that the number that I'm looking at? Like, for example, 59. Is it 1 less or 1 more than a multiple of 6? Well, 6 times 10 is 60, so it is 1 less. So yes, it could be a prime number. And then if I wanted to check, to make sure, it only has 2 factors, 1 in itself. Right? So, questions about that one? A composite number is a number that has more than 2 factors. And composite factors, they create colorful rainbows. So why do they make colorful rainbows? Well, because the number like 25, for example, is a square number because it's 5 times 5, which is a little rainbow. But the 1 times 25 is the overarching rainbow. So for example, if we look at the number 36, we know the factors are 1 times 36 for sure. So we put them on the outside. Do we think that 2 goes into 36? Yeah, we do. So 2 times what will give us 36? 3 times what gives us 30? So those help us with, that rainbow helps us with all the factors. Okay? So do use that rainbow when you're doing this. I really do like the factor rainbow. It really does help kids see, is this a factor of the number? And so then with multiples, there is also an interactive for multiples in the interactive glossary that on Alberta Ed's website. So do use it. But a multiple is a natural number that's a product of another number and itself. So for example, the 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9. And these are all multiples of that number. Okay, and the greatest common factor, it's the largest number that exactly, not evenly, but exactly divides 2 or more given numbers together. So you could also go to the Alberta Ed website because it actually will help you with doing that also. So for example, well, I just did this one here where it's number 2 at 12 and 18. And so it lists all of the factors of 12, lists all of the factors of 18. You see the common factors are 1, 2, 3, 4 is not common, 6 is, 9 is not, 12 is not, and neither is 18. So that means the greatest common factor is 8. Okay. Like really, we've got so much that we can use. I also think of the fact when I was a teacher in the 80s, we didn't have these interactive sites, which I wish now that we really did, because it would have sped things up. I had to do a lot of thinking on my feet too when I did this, but it's here. It's wonderful. Like I'll just go to, oh, I didn't put the link. Okay, so grade 5 is the divisibility tests. Now, if you were at my session on Monday, we talked about multiplication, and multiplication, those strategies really, really lend themselves into divisibility tests. So you need to have an intuitive understanding of this outcome, meaning that the meaning of the verbs investigate and generalize are provided. And so investigate and generalize, please do go to Tammy's action cards, what it means. So investigate means that they have to look into, we're not just going to give them these tests. They have to investigate and find what they are, and they have to actually generalize the tests for 2, 3, and 5. Okay, they have to make a conclusion. What are the things? So investigate is to carry out a formal inquiry or open-ended exploration in order to uncover facts and draw conclusions. So they will use their own knowledge and reasoning. And investigating differs from problem solving in that there's not necessarily one way of working out the answer. Okay, so generalize is to become aware of a pattern. Just like when I was doing prime numbers, I generalized because I saw a pattern that happened when I used this a column of 6 columns. I did not see that when I was doing the 10 columns. And so I did a lot of investigating. I did a lot of playing with that. And when I did that, that's when I saw that there's so much that I could do with that. And I generalized. Okay, so these were the number fact strategies. We used, for the 5 facts, we did use the tens. What we did was we multiplied by 10 and then halved the product. Generalizations for 1s and 0s. But for doubles, we doubled it for the 2's facts. We doubled it twice for the 4's facts, and we doubled 3 times for the 8 facts. And for the 9 facts, what we did was we multiplied by 10 and we took away a group. And for the 6 facts, we multiplied by 5 and added a group. So that, knowing that, and then when we're going into division, it also helps to do it that way, also to do those divisibility things, same clusters when using division. And so I gave you, if there was anyone here that did not come on Monday, these are the strategies for multiplying. And I've given you that in your link, in your document. And I will just go there one more time, just in case someone did not get it. But this is the link with all of my links for today's session. But let's just go on to divisibility tests. So these are the ones in blue are the only ones that you really need to know for grade 5. But I'm going to tell you, it's really, I don't understand, but you need to know these for grade 6. It's not written in any of our outcomes, but in order to do your prime factorization and to do divisibility, you need to know these divisibility rules anyway. So the divisibility rule, and kids would find this if at the pattern, and you want to ask yourself, will 2 go into this number, especially when we're doing those factor rainbows? Does 2 go into that number? How do you know? What do you notice? Well, if that number is even, 2 will go into it without a remainder. 3, if the sum of the digits is a multiple of 3. I'm going to go through that in a second, but that is a great way to check if 3 actually goes into a number without a what's it called? Remainder. Divisibility test for 4 is if the last 2 digits are divisible by 4, which means that you can have them twice. Obviously, if you did the multiplication and doubled it twice, it just means you're having it twice. And it's only the last 2 digits, that's numbers inside numbers, that help you with that. And then a 5, for 5, it is if the number ends in a 5 or a 0. Okay? 6 is really easy. Even though we don't have to make in our outcomes, it's not specified 6, but honestly, the divisibility test for 3 is if it has to be even first. Secondly, the sum of the digits is a multiple of 3. And I'll show you what I mean, what the sum of the digits is in a minute. But the divisibility test for 8 is that the last 3 digits can be halved 3 times, just the last 3 digits. And number 9 is if the sum of the digits is a multiple of 3. And 10 is if the number ends in 0. Now, you'll notice I missed 7. It's not a really easy one. I've never used it, and I never had to use it, and so I never put it on there, but it's something about you have to double it and subtract something, and then you can figure it out from there if it's a multiple of 7. I didn't put it on there, but you could look it up. There is one, but there's not a really quick and easy one to figure out. So again, I love digital root stuff, and digital root comes from this book. It is by it's by Kim Sutton. If any of you ever go to any of teachers convention and Kim Sutton is there, you can see her and you can actually buy this book from her, but I also put the link to her website. I had these huge aha moment when I found out about the digital root. And so the divisibility tests from using the digital roots is it has to be an even number. So it ends in a 0, 2, 4, 6, 8. A 3, it has to have a digital root of 3, 6, or 9. The last 2 digits for 4. If you want to know, does 4 go into it evenly? You just look at the last 2 digits. And if you can have the last 2 digits twice, then 4 will go into it without a remainder. 5 or 0, again, I went through this on the last page, but instead of saying the sum of the numbers, I've now used the actual word. It's called the digital root. And so what are digital roots? Well, digital roots, they're the sum of the digits in a number. Every single whole number has a digital root. The fast and lazy way to find a digital root is to add all the digits in a number until you get a single digit number. So the digital root has to be between 1 and 9. It's a property of every single number. That's why I thought I'm going to put it in here. It's one of the most helpful and important properties the numbers can have, and every number has one. And so again, my mind goes, why isn't it in our outcomes? Because it really is an important part of the number theory. And so Here it is. What is it? If I was to go through I actually have a session that I spent an entire hour on digital roots, which I will not have time to do that, but I just want to tell you what is it, and we would experiment. And what it is that what you do is you remove from the number all the groups of 9, and whatever the leftover is the digital root. So for example, 10 is 1 more than 9, and the sum of the digits is 10 plus 0. I'm sorry, is 1 plus 0. Okay, 1 plus 0. And so the sum is the digital root of 10 is 1. 11 is 2 more than 9, and the sum of the digits in 11 is 1 plus 1, which is 2. So that means when I removed the group of 9 from the 2, I'm left with 2 leftovers, right? But I can easily find the digital root by just adding the digits. So 12, add the 2 digits together in 12. Oops, not 11 plus 1 plus 1. It's 1 plus 2. The digits in 12 is 1 plus 2, so it's 3. And there is a pattern. Do you see that pattern? You remove the groups of 9, and whatever you're left with is the digital root. But there's a really easy way to find the digital root. You just add the digits in the number, the sum of the digits. So when we get to double-digit numbers like 18, we look at that and we add the 2 digits together, and we get 1 plus 8, and that's 9. So the digital root of 18 is 9 because we removed one group of 9 and we're left with 9 more. 19 is 2 groups of 9 and 1 more, but if we add them together, we go 1 plus 9 gives me 10, and then we still have a digital root has to be between 1 and 9, and so I just add 1 and 0 together and I get 1. And it's in the base 10 system. It's the removal of all the groups of 9 from the number, and what remains after the last group of 9 removed is the digital group. So it's a number, and if I wanted to look at how many groups of 9 are there in 105, what I look at is say, okay, well, 10 groups of 9 is 90. And well, one more group of 9 is here. So that means 11 groups of 9. And then that's 99. What do I have left over? 6. And so the digital root is 6. But if I was just to add the numbers together, I could say 1 plus 0 is 1, plus 5 is 6. I've got it. Okay, now that you have the foundation or understanding of what is it, let's just work on the digital root. Why do I want you to know it? Well, you know what? You can use it to check addition. How many times do you give us kids work and then you say, did you check your answer? And they say to you, okay, I have to go back. And what do? They redo the question again, right? Well, watch this. If I do 32 plus 11, the sum is 43, right? But I can use digital roots to find the answer. The digital root of 32 is 5. 3 plus 2 is 5. The digital root of 11 is 2, which is 11 is 2. Now add the 2 digital roots together. And what do you get? 7. What's the digital root of 43? Yeah. If the digital root is the same, then your answer is correct. What about subtraction? 32 minus 10. Well, the difference is 22. So the digital root of 32 is 5. The digital root of 10 is 1. 5 minus 1 is 4. What's the digital root of 22? Is this cool or what? Okay, does it always work? Let's try the digital root of 62 and we do minus 12. What's 62 minus 12? Anyone? 50. Okay, what's the digital root of 62? 6 plus 2 is 8. What's the digital root of 12? 3. What is 8 minus 3? 5. What's the digital root of 50? 5. Did it work? Uh-oh, let's try this one. 13 minus 4. Looks easy, doesn't it? What's the digital, what's the answer? Okay, well, let's figure this out. What's the digital root of 13? What's the digital root of 4? What's 4 minus 4? Oh, no. Now what? Does it work for subtraction? Do you think it doesn't work? Well, in math, it teaches us the power to persevere. Math is something, and I have to tell you, yes, it does work. Now, we need to find the pattern in this. And can we use digital root to check subtraction? Of course you can. Of course you can. But you have to look at the relationship of the digital roots. And in this situation, the digital root of the difference added to the digital root of the minuend is the digital root of the subtrahend. What? What are you trying to say, Yolanda? Well, there's some definitions we need to know. So minuend is the first number in a subtraction question. The subtrahend is what we're taking away from the minuend. The difference is what we're left with, right? But we also know that if we add the subtrahend and the difference together, what do we get? The minuend, right? So we know 4 plus 9 is 13. So what we're going to do is we're going to work backwards. We know that subtraction is closely related to addition. In fact, they are inverse operations. So what we're going to do is we're going to work backwards. So now let's do that question. Like I said, 13 minus 4. What is the, no, that one, sorry. What was the one I wanted to use? Sorry, I went back. Let's do it with, where's those numbers that I had on there? 75 minus 25. Okay, so 75 minus 25 we know is equal to 50, right? What is the digital root of 75? 7 plus 5 is 12, but we need a number between 1 and 9, so we have to make sure we add 1 plus 2 together and we get 3. So 3, I'm going to go, I need to get my drawing tool out here. I'm sorry. Draw. Okay. This is 75. This is 50. This. Oh, sorry. Erase, because I gave you a different number. Okay. Oops. No, that's not what I want. I want to draw. I want to draw 75, and I said minus 25. Is 50. So what's the digital root of 75? 7 plus 5 gives me 12, which means it is 1 plus 2, and that's 3. And 2 plus 5 is 7. What's the digital root of this? And again, something happened here. Something didn't work. Why not? Did I do this right? 2 plus 5 is 7. 7 plus 5 is 12. 1 plus 2 is 3. 5 plus 0. Something is, should 5 plus, oh yes, sorry. 5, and add up. 5 plus 7 is 12. And what's the digital root of 12? It's 3. So is 3 the same as this 3? Yes. Okay, why am I teaching this? Why am I showing you this? I honestly love it because now we're going to go on and I just need to erase this. Oops. Come on. I just want to erase this. Okay, next. Oh, erase my board. How come it all of a sudden it's not letting me erase? Clear all my drawings. There we go. And now, what have we learned? We've learned that every number has a digital root. The only possible digital roots are 1, 2, 3, 4, 5, 6, 7, 8, or 9. We've learned that every digital root is a property that a number has. They're really helpful for checking computation, like adding and subtracting, but they're really helpful for when we're doing multiplication. Same thing here. We can check when we are doing multiplication. So what is the digital root of 22? It is 4. Digital root of 7 is 7. What's 4 times 7? 28. Let's check, and we could also check to see the digital root of 1 plus 5 plus 4 is 10. 1 plus 0 is 1. What's the digital root of 28? It's 2 plus 8 is 10, which is 1 plus 0 is 1. And so I can, when I'm checking my work, I can see, yes, it does work. Absolutely, it does work. And then we can also look for patterns on the hundreds chart. So I can say, if I wanted to do all of, on a hundreds chart, I could just color in all those numbers that have a digital root of 1. So for example, all these numbers have a digital root of 1. Here's all the numbers now that have a digital root of 2. And what I'm going to see a nice visual pattern that's showing up on my hundreds chart. And it is amazing. And I can keep going and going, and then I can find that all the patterns will work this way. So what is the digital root for multiples of 3? Very simple. All of the digital multiples of 3 either have a digital root of 3, 6, or 9. So if you are doing divisibility tests and you want to know, will 3 go into my number? Will 3 go into my number without any remainders? What I would do is I could just do a digital root, and if it is a 3, 6, or 9 of that number, yes, it will. So if numbers, all numbers that are multiples of 3 have a factor, or have 3 as a factor, have a digital root of 3, 6, or 9. And there's no patterns with the digital root of 2, 5, or 10, but that's okay, because we know that for 2, it has to be an even number. We know that the divisibility test for 5 is it has to end in a 5 or a 0. And we know that the divisibility for 10, it has to end in 0, right? So we've learned so much about digital roots, and we know that we can use them for checking computation like multiplication, and we know it works for addition and subtraction. And yes, I'm going to tell you, I'm not going to show you, but I know I can tell you, you can use digital roots to check division also. I love them because you can use them, digital roots, for divisibility facts. And you can also use them to explore for factors. And so when we look at this, we can see I can use my knowledge for doing divisibility tests, for digital roots, for factors. And when I know that, then I can have way more success in listing factors also for numbers. So then the other thing that comes up is, why can't I divide by 0? Kids will often ask us, why can't you? Well, the whole thing is, think about 12 divided by 3 gives you 4. Why? Because you have to multiply 3 by 4 to get 12, correct? So it does divide because there are 2 factors I can multiply together to get that number. How about 12 divided by 2? Can I divide 12 by 2? Yes, because 2 times 6 gives me 12. 12 divided by 1 is 12. Why? Because 1 times 12 is 12. Whereas, can I do this? What would I multiply 0 by to get 12? So I can't divide by 0. But 0 divided by 3 is 0. Why? Because if I multiply 3 by 0, I get 0. And so I can say 0 divided by 154. Yeah, I can do that because I can multiply 154 by 0 and still get 0. Same thing here. But the big thing is, I can't divide by 0. Why? There's no number that I can multiply by to get that number. Correct? So grade 6. Grade 6, you have basically 2 outcomes, and one of them is analyzing numbers using prime factorization. And once we learn how to do prime factorization, then we also have to teach exponentiation. And so what we do is we break down numbers into their prime factors. So you can see from grade 4, they've learned what is a prime number. Now we want to make sure that they understand that in order to do prime factorization. So this is a great tool, beautiful tool on Learn Alberta. And if I go to Learn Alberta and I open up, hopefully I don't have to sign in again. Oh yeah, of course I do. I'm going to log into my account, use my Google sign in. I'm going to go to here. I thought, see, I had them all open because I thought I'd show this. Okay, it's a gizmo. This is beautiful to help things. And then there are 2 gizmos for this, one for students and one for teachers. The one for teachers, it gives you, if you go up to the lesson info up here, it'll show, okay, this is, I actually have the student one open. I'm going to go to gizmos to do, oops, no, okay. This is the teacher one, looks exactly alike in that, but you will find here, there's an answer key and there's a teacher guide. But everyone, there's a student exploration sheet and vocabulary sheet, and I'm going to show you how you can use this. I am going to pick a number like 30, what was the number I had here? 36. So I am going to choose the number 36. Now you can see that the prime numbers are in yellow. The composite numbers are in blue. So I am going to clear this page and only 2 to 99 things. So I'm going to make the number 36. So I want to pick two numbers that I can multiply together to make 36. So does that anyone want to give me one of them? You can just put your mic on and just speak.
6.
6? Okay. So you have chosen 6. So 6 times what gives me 36?
6.
Okay. I'm going to put that in there. But they're both blue. I want to end up with only yellow numbers. So what two factors can multiply together to make 6?
2 and 3.
Okay. So I'm going to 2 and 3. 3 and so the prime factorization of this is 2 times 2 times 3 times 3. This is a great tool to use because they need to end up with just the prime numbers. Now, if you look at this one, this is different from the way I did it. I did 2 times 18. And then I had to break down my 18 to 2 times 9. And then I had to go 3 times 3. Now, this is beautiful to show that there's more than one way to get to the prime factorization. Okay. The other gizmo that you can use is using the area model, which looks like this. I think, did I put this? Oh, yeah. So there's that link. And then the area model, I forgot to put it on here. So I'm just going to copy that and put it into the document. Okay, so just to give you an example, this one is we're factoring 50. So I can go 2 times 25 here. And I could show that one of the areas is 2 times 25. The other thing is, watch. Oh, I love this part. It's also 10 times 5. Or, okay, then how about, so the prime factorization is 2 times 25, is 2 times 5 times 5. And then let's just say, let's do 100. So, come on. There. So I can do this if I just choose 2 times 50, but then I might want to change that up if I would have started with that. Come on. There. So I can we can show the area model for different types of factors also. I totally love what Alberta Ed has purchased for us teachers in Alberta. This is from Explore Learning, and instead of us buying it, it is on Learn Alberta, but you have to use it. I have to tell you, they do have a count of how many times things are used, and if they're not being used by Alberta teachers, we're going to lose it. Okay, so please go on, have your kids use it, etc. It's a wonderful tool for us to have. And then once we do prime factorization, then we also have exponentiation, and we want kids to understand what is a power, and I want you to know that also exponents are part of your grade 6 algebra unit, so you need to know that we need to go into that also at that time. And so powers and exponents, I know that a lot of teachers call this whole thing here, like 5 to the power of 2. They say 5 to the power of 2, and this is the exponent. That's not the exponent. That's called the power. The exponent is the number that indicates how many times we multiply the base by itself. And so 5 to that has a 2, 5 to the power of 2, or 5 to the with the exponent of 2 means 5 times 5. And so one of the things that kids will often get mixed up is they will think that that means 5 times 2. And so multiplication of whole numbers is repeated addition. So it is 2 plus 2 plus 2 plus 2. So it's 2 times 4. But an exponent is repeated multiplication. And that is 2 to the power of 4, which is 2 times 2 times 2 times 2. Okay? And so now once we have our prime factorization, once we've done that, then we say, let us now give this answer as a product of prime numbers. And it would be 36 is equal to, with an exponent of 2, times 3 to the power of 2. Okay? Same thing. What is the prime factorization of 40? Well, the way I have figured it out, the way I did 2 times 20, and then I broke down the 20 into 4 times 5, and then I broke down the 4 into 2 times 2. There are many ways I could have done that. I could, if I go up to here again, I could just say clear this. I could say choose the 40. I could say that that is the same as, no, I'm going to choose 4 times 10. Oops, 4 times 10. And then I would have to do this. And then I would have to do, and oops, I need to move this over a bit. I know what I did wrong there. How do I erase that? 2 times. Okay, ignore those two. And so it is 2 times 2 times 2 times 5. But you'll notice I still have the same thing, 2 times 2 times 2 times 5. Didn't matter how I broke it down, but now I see it's 2 to the power of 3 times 5. Okay. I also there's lots of games that I am giving you, but does it divide? You just need to have make a cube that is 2, 3, 4, 5, 6, and 9. So just get a cube. Dollarama sells them, and you just put the 2, 3, 4, 5, 6, and 9 on them, and you roll it. And you can play in things. So for example, this is where you can test your divisibility. And so if I roll a 9, what's a divisibility test for 9? The digits have to add up to 9. And so you have to find a number where digits add up to 9, and there's one right there. I can roll again. I roll a 2. What's a number that 2 goes into? And the second person would just find another thing here. So the winner of this game is, you're the teacher. You decide. It could be 4 in a row, 4 squared, It could be anything you really want it to be. It could be whoever has the most chips on the um, on the card in 10 minutes. You may time it, but you decide, because remember, you are the adult in the room. Another game, okay, again, here's 3. So what's the divisibility rule for 3? If the numbers have the digital root has to be a multiple of 3, right? It has to be a 3, 6, or 9. Another game, this one is really hard. I'm going to tell you right now, it is hard. So again, using those same cubes, what you're going to do is you place, both players place a thing on 15, and you take turns to roll the cube, and you divide your number in the space by the number on the cube. And you get to move the number of spaces equal to the remainder. So, for example, if I start here, and let's say, I don't think I have, no, I don't. Okay, let's say I'm on 17. Let's say I rolled a 2. 17 divided by 2 is 8, and I have 1 remainder, right? And so I would be able to move it only 1. But if I rolled a 9, 17 divided by 9 is there's only 1, but it has a remainder of 8. 8 is 1, 2, and then I would move that. So anyway, the other thing that didn't come up is square numbers. And that's when we're multiplying, we can help kids understand a square number is any number that when you multiply it, you can actually, if you were to make an array, it would make a square shape. And that's why they're called square numbers. So the first 6 square numbers in ascending order are 1, 4, 9, 16, 25, 36. And Carolyn, you had something that you just said that's interesting. I just want to read it. Oh, so will they give free access to all Alberta teachers, Carolyn? Interesting. Okay. I don't know, like if you go to their website, okay, let me just find where something just
Sorry, I was just trying to find the unmute. You asked me a question. I'm like, I don't know how to unmute. Just when I went to the Gizmo session, she says, if you log in this way, you'll have access to more. And then I tried when I was searching for things to support various units, and I found it to be true. But there's, if it meant not losing gizmos that I had to log in through Learn Alberta first, maybe I would, and then go back and log in the other way. I don't know.
Yeah, well, I'm going to put the link into our document here. That's a really great thing. That's a really good thing because it does say sign up for free. One of the things I do like about Learn Alberta is it does line it up with outcomes.
Yeah. I had another question to do with the curriculum and exponents.
Okay.
Just because I'm sure that I understand it correctly. So I'm just going to the window here. When it says repeated multiplication of oh my goodness, end of day, identical factors can be represented as a power. Is it really just that the idea that when they make a factor tree, if you see, 2 times 2 times 2 times 3, that they would just realize that you could represent 2 times 2 times 2 by, 2 to the power of 3?
Yeah.
So, but they're not necessarily saying, okay, now we're going to give you, like all these numbers to the power of something, and they're expected to do it the other way, where they been 2 to the power of 3 and calculate,
Not yet.
Okay, so just the fact that when they make a factor tree, they could represent those repeating prime numbers in that way.
Yep. They will, when the, Carolyn, do you teach grade 6?
Yeah.
Okay. When they get to algebra, they need to actually learn how to make that number. So if it is 2 to the power of 3, they need to know it's 2 times 2 times 2 and actually find that it is 8.
Okay, and that's part of why I was asking, because exactly algebra, order of operations used to be everything except exponents, and now it includes exponents, but it doesn't specify like exponents to what extent. And so in my head, I'm like, you'd only make them do like square, right? But that may not be the case. And I don't know, it doesn't specify, when I go to algebra, it doesn't specify exponents,
Like what?
exponent, or
Well, honestly, if like, my opinion, and again, I don't know for sure, but I can find out. I could ask. When we are working with kids that are in grade 6, we're talking about 12, 13-year-old kids.
yeah.
I'm not going to give them a number like 75 to the power of 2 or 75 to the power of 3. Not going to do that. But I will give them 2 to the power of 4, 5 to the power of 2, 6 to the power of 2. I might even go 6 to the power of 3. But I'm going to be careful. I wanted to, my goal is, do they know what it means? Because in the end, what I want to know, what I'm going to work on, is when they get to grade 7, then they're going to be able to use a calculator. And if they know it's 75 to the power of 2, they can put in 75 times 75. But I want to make sure that they actually know what a power is and how to simplify it. Okay? So, anyway, yeah. So these are your square numbers. And then, oh, how come this is showing up again? Good Lord. Okay, so I cannot believe it. It's 5 after 5 and I'm done. So thank you very, very much. Oops. That's not what I meant to do. All I meant to do was